Let's start off. So, ADS3. Pure 3D gravity. Let's see. So, as I just said, can we compute some wormhole amplitudes in pure three-dimensional gravity? And by the usual theorem that when you pose a question like that in a talk, the answer is yes. The one I'm going to talk about is the one that I have computed with Jordan, which is analogous to the double trumpet of JT, if those words make sense to you. So the one that we computed was one that has two boundaries, each a torus, connected smoothly in the interior in such a way that the Euclidean geometry is that of a two-dimensional torus times an interval, at least topologically. And the thing that allows us to proceed to compute this thing, even though this is a completely off-shell problem in 3D gravity, there's no classical solution to Einstein's equations that has this topology. How do we do it? Well, okay, here we go. We exploit the fact that topologically, this is an annulus times a circle, which we can interpret as Euclidean time, and we quantize along the circle. Roughly speaking, what we do is a canonical quantization. That's roughly, you'll see the idea how we do it in more detail shortly. This is technical, so my apologies for dumping a lot of technical details on you. I'm going to try to keep it as simple as possible while giving you the highlights. But I think it's worthwhile to see, it's what's involved in trying to compute some of these things. I'm also very proud that we were able to do it, so I'm very happy to share it with you. So the way we proceed is the following.
Sorry, quick question.
Yes.
You said that this is like the double cone?
Double trumpet.
Double trumpet. Ah, cool. Okay, perfect. Nice. Thank you.
Yeah. Right, so we're going to compute it first, and then we'll discuss physics encoded by it. Maybe one other comment before proceeding. Now that we're getting past history and into the current day, of course, there's been an explosion of activity. Lots of people have been working on this. There's been some fantastic papers just in the last couple of months. I'll allude to them briefly later, but in general, my apologies to when I don't write down references, especially if you're in the audience. There's been a lot of fantastic work, not just these papers, but time is limited. So the way we proceed here, we need to work intelligently and creatively to go off shell. How are we going to do it? Well, the way that we're going to do it is as follows. 3D gravity can be recast famously in Chern-Simons-like variables. This was originally pointed out in old work by Achukaro and Townsend, and also Witten back in the 80s. And, well, it's led to an enormous source of confusion, actually, over the years. Because, okay, well, is 3D gravity a Chern-Simons theory? Is it gravity? It's gravity. But we can recast it in variables that resemble those of Chern-Simons theory. But really, the kind of functional integrals we're going to do are over gravitational degrees of freedom. So the way this works, though, just to remind you, or to say it if you've never seen it before, we're going to work in first-order formalism. And what I'm going to do is to start in Lorentzian signature and then analytically continue to Euclidean along the way. And in Lorentzian signature, first-order formalism, what are we dealing with? Well, what are the variables? Well, instead of a metric g mu nu, what you have are a dry bind, 1, 2, 3, and a spin connection. You decompose the metric into driveline. That leaves the redundancy. Under local Lorentz transformations, you have to gauge that. Spin connection is the associated connection, whose curvature is Riemann tensor, once you use the driveline to turn it into an object with 4 space-time indices. And if you write down the Einstein-Hilbert action with cosmological constant in these variables, 1 over 16 pi g in Lorentzian signature, there's a plus d3x square root minus g r plus 2. You can rewrite this in terms of Chern-Simons like variables, AA and A bar A. If you want, you could use a tilde. These things are real. They're not complex conjugates of each other. We just have 2 of them. They look very similar, so we have to indicate that somehow. Where this is 1/2, we use the 3-dimensional epsilon tensor. I'm writing these as forms. Form linear combinations of spin connection and driveline. If we were to restore the ADS radius, then it would appear here. And then what we do is we define SL2R valued 1 forms, AA, JA, and A bar, A, J bar, A, where J and J bar are generators in the fundamental representation of SL2. We assemble these things into 2x2 matrices. And when we do that up to boundary terms, this action up there can be rewritten as minus k over 4 pi difference of Chern-Simons actions for A and A bar, plus boundary terms. Does this mean that gravity is Chern-Simons theory in 3 dimensions? No, it does not. But it means we can write it in a way that resembles Chern-Simons theory, and that's very useful for practical computations, as we will see. What is K? K is 1 over 4G. One question you could ask off the bat, we're used to in Chern-Simons theory, the Chern-Simons level, the coupling constant in front of action being quantized. Is this quantized? No, it is not quantized. However, if you had included a gravitational Chern-Simons term up there and rewrote things in Chern-Simons-like variables down here, that would be indeed quantized, but that we knew already in order to make sense of gravitational Chern-Simons term in the first place. So what next? Well, I said that for the wormhole that we want to compute, we're going to separate, we're going to use that, at least in the Euclidean signature, the topology is that of annulus times circle, where the circle is Euclidean time.
Question.
Hang on just a second, let me finish the thought, and then I will be very happy to answer the question. So what we're going to do here to proceed is we're going to treat time separately as an intermediate step. We're going to separate the 3 coordinates into time, which later will analytically continue, and some spatial directions. Go ahead.
Sorry. There is a prescription to quantize Chern-Simons theories, right?
Oh, yes.
So why do you say that specifically is not quantized? Cannot be quantized?
Okay, one sort of reason why you should think be careful, and you give pause. In gravity, we don't just have an action that looks like this. We also have gauge symmetries. We mod out by diffeomorphisms and local Lorentz. Whereas if you were to treat this as some kind of Chern-Simons theory, non-compact Chern-Simons theory, you would mod out by gauge transformations. You can ask, are these things the same? They're not the same. They're the same on shell, which is to say then that there is a sort of semi-classical equivalence between these two theories, but there's no guarantee that that will be true off shell. And since we're dealing with a wormhole, then okay.
Thank you.
Hey, so yeah, in gravity, whenever we think about the action and doing the path integral, it involves this sum over very different geometries. Whereas in Chern-Simons, we don't have that, right? We have some background. How does that?
Yeah. So again, this is just a rewriting. So indeed, I'm not. How to say, that would be another issue that you would run into if you tried to say, oh, gravity is equivalent to Chern-Simons. In gravity, you would expect to sum over topologies. What does that mean here? I mean, look, there's other issues. People fought and argued about this for years, and were very confused. For instance, in Chern-Simons theory, you would integrate over configurations like A equals 0.
Yeah.
Which would be a singular spacetime from this point of view. So what the attitude that I'm going to take today, and what we did in our papers, is this is a rewriting that I'm just exploiting to, when we canonically quantize, we're gonna have some constraints. I'm just using that as an efficient means to solve the constraints. That's the only thing. Otherwise, everything I'm doing is going to be path integral over first order variables.
Should I think of this Chern-Simons rewriting as having some fixed background, and then it's the fields on top of that fixed background?
No, I mean it's algebra is all that it is. A and A bar are linear combinations of first order variables, and this is just really an algebraic statement that these two actions are equal to each other.
I guess the thing that's confusing me is like when you define Chern-Simons, you have some manifolds. Right, and is there some manifold, in this rewriting, did we get a manifold?
No. On a space-time of fixed topology, and for a specified, you have to specify the field configurations on that manifold. This is an algebraic statement.
Okay, thanks.
Okay. Right, so we're going to separate out time from space. And why is that useful? Well, okay, we have to talk about some old things. There's a lovely old paper of Elitzer, Moore, Schwimmer.
Sorry, I see there is a question in the chat, but it's a long one. Let's see. So the picture of wormhole that you have shown earlier was boundaries are torus with an interval connecting the boundaries. There may be the possibility that one can construct similar picture with other topology of the boundaries. For example, S2. How can one know that, yes, the solution is a consistent wormhole solution?
Right.
Are there some conditions that have to be checked? Yeah.
Right. So in general, one can consider things that are topologically higher genus surface times interval, or genus 0, as in the question in the chat. Genus 0 is unknown, can't be computed by the methods that I'm describing so far, so it's unknown. G equals 1 is this talk. G bigger than 1, well, how to say, remember I said last time that at least within string theory, there are saddle point wormholes of this sort, quotients of hyperbolic space. They're unstable to brane nucleation, so their fate within string theory is, if you have a runaway, then it's completely unstable, and if it's stabilized but very large, then endpoint of instability is not known. People argue. but if we're just talking about pure 3D gravity, there's nothing illegitimate about those. And in that case, you have saddles, honest-to-God saddles. They have been a major player in a recent paper that I was going to mention later, but I guess I can say now, of Chandra, Collier, well, also, sorry, first, before them, Bolin and De Boer, but then also another paper from earlier this year, also Hartman and Maloney, where they, how to say, where they study them semi-classically and at one loop. Hope that answers the question. All right, so we're, this is us today, though. What's the story? So, as a warm-up to the thing that we really want to do, where we have annulus time circle, suppose that we were dealing with an actual Chern-Simons problem with compact gauge group G on disk times circle or times time. What happens in that case is that one can rewrite the Chern-Simons action up to boundary terms as Chern-Simons level over 4 pi d3x spatial epsilon symbol trace a naught spatial field strength minus AI AJ dot. And why is that nice? Well, notice that A naught takes the form of a Lagrange multiplier. So you can integrate it out. What does it do? It enforces Fij equals 0. Now, if you want to do this honestly, you have to worry about gauge fixing. This is gauge theory. And if you worked in a covariant gauge, this would not be the only term involving A naught in action. You'd have to work harder. But you can pick other gauge choices of gauge, like Coulomb gauge in this setting, where A naught, the only term that it involves is this one. So you integrate it out. That enforces Fij equals 0 as a constraint. And that can be solved. This is, flat connection. We know what flat connections look like. This implies that AI takes that form, where G is single valued. And what happens in this case is the Chern-Simons theory reduces to a boundary chiral Wessamino-Witten theory, a theory of the boundary value of G. It can be evaluated. If we were doing Chern-Simons theory, then still, for the annulus times time, what happens? Well, the same kind of thing happens, except now the space, the constant time slices are annuli. So let's call the direction that goes around x, with x being 2 pi periodic. Well, now the Chern-Simons action still looks like this. You integrate out A naught. It still enforces spatial field strength equals 0 as a constraint. You still solve it, but now there can be a holonomy in the gauge field. Which I denote, in other words, G need no longer be single valued. When you end up you can play some games and you can recast this G tilde in terms of a piece that is not periodic around the X circle. It can depend on time. Times a piece that is periodic, that is single valued. And then what you get, you take Chern-Simons, evaluate it on this, It reduces to a boundary effective action that depends on G over here, G over here on that boundary, and this lambda of T, this holonomy. The effective action that you get is equivalent to a WZW model. G1, well, one of these, how to say, in the canonical presentation becomes a bunch of left movers around one boundary, and G2 a bunch of right movers. Another way of doing this that is better adapted to what we want to do in gravity, if you were to pick something like outgoing unit normals and fix that the boundary over here, how to say, this is a constant time slice, but the three-dimensional geometry on which this would be living is the same kind of thing that we drew earlier. And if you fix that the complex structures are different, tau 1, tau 2, and you pick outgoing normals instead of like the canonical presentation is both are kind of going in the same way, then you can use this boundary effective action to compute Euclidean partition function. And what you get in that case is what happens is this lambda ends up being, how to say, you functionally integrate over time-dependent lambdas, but the path integral localizes to configurations where lambda is constant, and in fact where lambda is quantized. And you end up with a sum over those quantized allowed values of lambda. And what you get then is character of representation of a one-loop corrected G level, I'm calling it K tilde, current algebra, Kac-Moody algebra, where lambda indexes representation, an integral representation of that Kac-Moody algebra. And then something for the other guys. And where this comes from, as I said, lambda localizes to constant values, constant quantized values. K, the Kac-Moody level basically gets a one-loop shift. And this character here comes from functional integral over G1. It just produces a character. And the other guy comes from integral over the other fluctuations, G2. And it's very, like, I'm stating the result because, getting it, we can talk about it after, over lunch if you want. It takes some legwork, but it's actually quite straightforward. Yes? Right, so you stick this into here. That's gone. This, it turns out, becomes boundary term, pure boundary term. You have to do the computation. It's not a long one, but I'm not going to do it in real time. Right, so physically a way of saying this is that you have a Hilbert space associated with this model, indexed by these different representations of Kac-Moody, and you have one for each allowable representation. Each representation occurs once in the spectrum. And it turns out that's exactly what's needed in order for this to be a well-defined, to get a well-defined two-dimensional CFT out of this, for it to be modular invariant. Now, that's what happens for Chern-Simons theory, compact Chern-Simons theory. We're not dealing with compact Chern-Simons theory, we're dealing with 3D gravity. But it works out in a very similar way to this.
Quick question.
Yes.
Could you explain again, like, why quantization is needed?
Why quantization is needed?
In other words, okay, I have some technical problems with reality. Like, I assume something like a monodromy sort of based matrix going on there, but you said, like, we get quantized levels out.
Yes.
What
I
said
was that the holonomy the monodromy ends up getting quantized.
What do you mean ends up getting quantized?
How to say, what do I mean? I mean that, I mean, at a more, there's, when you decompose fluctuations of G on the two boundaries, there's a particular combination of fields that you can, that appears that the only way it appears in effective action is multiplying lambda dot.
Okay.
And so it acts as Lagrange multiplier, setting lambda dot to 0.
Okay.
That tells you lambda is constant. But then not only that, the particular combination of modes involved is a compact, I mean, because the underlying G's are compact, it's a particular compact mode. It lives in some target space. And then that means that there's, in this, you should sum over winding modes associated with that compact scalar.
Okay, okay.
And then that sum over winding modes is what enforces not only that lambda dot is 0, but that the allowed values of lambda are, it's analogous to like particle in a circle in quantum mechanics.
Okay.
The winding modes there restricts the momentum to be, integer in some units.
So is there a analogous, like, simpler system?
Yeah, you do this for U1. I mean, I'm describing it for...
No. Yeah, I guess as you said, like a particle on a circle or something like that.
Yeah, that's right.
Okay.
So yeah, in that case, if you look at P Q dot, literally that, where Q is 2 pi periodic, you integrate over Q. What that does is that when you the effect, how to say, integrating out Q sets P dot equals 0, but then furthermore, the sum over winding modes for Q over the time circle will delta function localize P to integral values.
Perfect. Yeah, thank you.
Yeah.
So you did the analytic continuation somewhere, because at the end, are there any details that need to be informed there? Like, for Chern-Simons, it's non-trivial, right?
For Chern-Simons, it's, for Chern-Simons, all I'm doing is I'm analytically continuing the time. If I analytically, there's a whole literature where things do get very dicey on analytic continuation of Chern-Simons, but that's when you do things like analytically continue gauge group or level or things like that. But analytically continuing space from Lorentzian to Euclidean that's not subtle.
And also, you made this comment about how G1 and G2 should be thought of as one is left movers and one is right movers.
Right.
I'm a bit confused by that, because it seems like there should be like two separate WGWs, like one on the inner boundary, one on the outer boundary.
So
but they're not chiral WGWs,
they're
right?
chiral on each boundary.
They're chiral on each boundary? Why are they chiral?
The reason why, how to say, this is bulk action. There's also a boundary term. And what ends up happening, how to say, roughly speaking, is that on one, this term, you get, on each boundary, roughly speaking, you end up with something like a dxg inverse term in the effective action. But then from this, you get a plus or minus partial x g partial t g inverse, where the plus minus depends on which boundary you're on. And that's what leads to left, you combine those two things, there's an asymmetry, there's a chiral asymmetry that leads to left on one, right on the other. This is a very pedantic technical detail. That's like, when you integrate that thing to get a boundary action, you're using, Stokes' theorem, so you get boundary terms, and that how you write things depends on the choice of orientation that you endow the boundaries with. And the canonical one is where you kind of pick them both going the same way. That's where you get left movers on one, right on the other. The thing that's more natural from our point of view that we're going to be doing in gravity is you pick the outward orientation on both sides, and then they're both either left movers or right movers.
Last pedantic point, is that why there's only two characters there?
What's that?
Those characters are...
You get two characters, yeah. One for these guys, one for these guys.
Am I right in saying that it's 2 instead of 4 because it's chiral?
Yes.
Cool.
Yep. All right. Good questions. So now we want to do gravity. And I'm not doing well on time, so let's see. So in words, what do? We start from the Lorentzian theory on annulus times time. We continue to imaginary time. Why we do it this way, as opposed to just starting in Euclidean signature, I can tell you. But I don't want to stop the talk further. We also have to do something that we do not have to do in the pure Chern-Simons context. We have to impose boundary conditions at infinity. In particular, we impose the asymptotically ADS boundary conditions. Well, or the Euclidean version of that. And in practice, what this does, our boundary valued fields, instead of being like general 2x2 matrices, you get truncated to a bosonic degree of freedom on each boundary, a single bosonic one instead of 3. So we end up getting degrees of freedom you could call phi on the two boundaries coming from A, and what you could call phi bar coming from the other combination of first order variables. But then, if we're dealing with the annulus, we get the analog of this holonomy, time-dependent holonomy. You get one for each factor. We call them B and B bar. And, if you, at this point, I could tell you a lot or I could tell you a little. I'm going to try to skirt the line in between. The boundary action that you get for this field content is, roughly speaking, Euclidean signature, it's I, P, Q dot. This is P, Q dot in Euclidean signature, minus Hamiltonian, where phi bar, all this stuff describes both the position and momentum degrees of freedom. The action, in other words, what this really means is that the action takes a one-time derivative form, which you can think of as a Hamiltonian form of a path integral. The nice thing about that is that the PQ dot term it hands you a symplectic structure, which you can use to construct a measure. You can get the integration measure over the field from that. And I guess the form of the action is, look, I could write it down. It would take the whole board. It's not going to enlighten you. I'm going to just quote the answers. The one thing I guess I should say is that these fields, phis and phi bars, they're non-standard bosonic fields. If we talk about phi 1, phi 2, and B at fixed time, this is an element of a funny coset, diff S1 times diff S1 times positive numbers divided by U1. So these are, roughly speaking, diff S1 fields, except you have to be careful about global issues, and the B is non-negative. How do you know that? When you reconstruct the three-dimensional geometry that corresponds to these guys, you see that, roughly speaking, B and B bar are controlling the size of a bottleneck in this geometry. And so if you want to integrate over non-singular geometries, those things better be non-negative. Somewhat miraculously, the path integral over all these fields can be computed exactly to all loops. It's one loop exact, in fact. And the computation of that path integral is a subject that's very dear to my heart, but it would take too long, so I'm going to skip. I'm just going to go straight to the answer. The answer for the whole amplitude depends on the two boundary complex structures. Also, they're complex conjugates, but I'm not going to write that. And it can be written as a sum over PSL 2Z images of a more fundamental object, where this Z tilde, what is it? It's a prefactor times a bunch of Virasoro characters. What are H and H bar and C? C is a one-loop corrected central charge, and H and H bar are conformal dimensions of primaries associated with this B and B bar. What happens is that in the path integral over B, B bar and the phi's, just like over here where the lambdas get set to be constants, over there the B's and B bars also get set to constants. And you can then relate them to some conformal dimensions. And this lower bound of integration corresponds really to integrating over non-negative B and B bar. So roughly speaking, where does this come from? There's a variable in phi and phi bar that sets B and B bar to be constant. And then this Virasoro character, this comes from the integration over phi 1, this from phi 2, this from phi bar 1, and this from phi bar 2. And you end up with this structure. Yes?
So from what you just said, it sounds like the path integrals factorize between the phi 1 and phi 2.
Yeah, yes. Well, they almost factorize.
Right, yeah, I was going to ask about the global...
They almost
global
factorize with the exception, so the exception of this, if you will. So from like a Hilbert space point of view, what ends up happening is that the Hilbert, you have movers on one boundary in some multiplet with some energy, some left moving energy, and they're associated with right movers whose descendants are completely independent, but whose primary is forced to sit in the same energy.
I see.
You can think of this as like a bulk Gauss's law. And we're kind of used to this. This is a very fancy way of saying something that's kind of intuitive and semi-classical, that when you like look at something with two boundaries, like a black hole, for instance, energy you see over here is the same as energy over here. This is a fancier version of that statement.
The other thing is that in this, we're summing over gamma. Is that gamma hiding in VZM?
I forgot to write gamma over here.
Ah, cool. Thanks.
Thank you. There's another question.
Where's the K dependence?
Come again?
Where is the K dependence? Oh,
It's the
Newton.
K dependence. The K dependence, I traded K, which was 1 over 4G, for the C.
So do you trust it for every C, or what's the...
That's the only way that the C appears in this expression. And in fact, okay, so I'm presenting an integral representation of the answer. You can do the integral, and then C drops out entirely. Essentially, I haven't written what the functional form of the Virasoro character is. It goes like chi, ch, these are ordinary characters. this is like product 1 to infinity, 1 minus q to the n, where q is e to the 2 pi I tau. And then there's a prefactor which has a q to the h minus c over 24. And so what happens is when you plug in the h here, but you integrate over these bounds, the c's end up, you can rewrite the integral in another way in such a way that c just completely drops out of the integral. Yeah, this is proportional to an eta function. So in fact, you can, here's an integrated form of the answer that you get. Z, tau 1, tau 2 is equal to, I didn't say what this was. I should do that first. What happens in these geometries is that there are certain zero modes of the gravitational field. And those zero modes, when you integrate over them, at one loop level, they're not Gaussian integrals, they just give you a volume factor. That volume factor is what I'm calling VZM, ZM for zero modes. Those zero modes, what they are translations of one boundary relative to the other. Those have finite volume. And if you compute this thing carefully, we worked on this paper for maybe 7 months. 3 months of it was getting this. It's a factor that depends on the m taus. The way to think about it is when the imaginary part of tau is like how big the thermal circle is on each boundary. When they're the same, this is proportional to m tau. It's proportional to how big the torus is in the time direction. And all that factor is then is, well, you can translate time on one boundary relative to the other by that amount, however big the time circle is. Okay, now with that, we can write this. This becomes 1 over 2 pi squared, 1 over root m tau 1, 1 over eta function, complex square, 1 over root m tau 2, 1 over eta 2 complex square, times sum over SL2 images, m tau 1, m gamma tau 2 over tau 1 plus gamma tau 2 complex square. And if you know anything about modular forms or 2D CFT, this is a pretty nice expression. Why is it nice? This is what you would call the partition function of a non-compact boson. Sometimes this language is used. That partition function, strictly speaking, doesn't exist, but this is what you would call it. At tau 1, it's modular invariant. So is this. All the Virasoro these in the infinite products that define these eta functions. What is this? This is the geodesic distance in the upper half plane between points tau 1 and tau 2, which, if you sum over images, is also modular invariant. In fact, doubly modular invariant under tau 1 and tau 2. So this whole expression satisfies something very important that it got to satisfy, which is modular invariance under independent transformations of the two boundary complex structures. It got to satisfy that because modular invariance is really, how to say, it's really just a statement that, if you put a conformal field theory on a torus, that you can parameterize the torus with the torus is parameterized by a lattice, and that lattice, there's Well, it's the lattice. You're defining on the plane modulo the lattice identifications, and there's many different ways to talk about those identifications, many different unit cells that are all equivalent to each other. Yes?
So related to the scaling of this partition function, I can understand why the integral is order 1. That's like, because it's one loop, essentially.
Yeah.
So it's independent of g, but usually you have like the classical term for the action. So here it's 0.
So that's the second very kind of interesting ex post facto fact about this expression. It has no dependence on g Newton.
Okay, so
That's not a, and that's, that is consistent with statement that there's no saddle point approximation to this amplitude. If there was a saddle point approximation, you might have hoped for, would have certainly had some g Newton dependence, but.
So in that case, in the JT discussion, we had a proper kind of expansion, which is the genus expansion, which showed us that this is the leading contribution to the connected part. Here, is there any other kind of thing that allows us to say that, well, other contributions are suppressed with respect to this?
Good. So is this the dominant contribution to the 2 torus partition function? One can answer to this is that one can take a kinematic limit for tau 1 and tau 2. In physical terms, you would be zooming in on the regime that if you had a single replica zooms in on near extremal BTZ. And in that case, there is a JT limit of 3D gravity. There's an emergent genus expansion. And you can say that basically, contributions from geometries of the form, sigma g times circle, where the spatial slice is a higher genus surface, that those are all suppressed. That's the best one can do. Because there's no analog of, there is no analog of genus expansion in 3D gravity. So that's the answer that one gets. Maybe another nice thing about it that's worth saying is that part of this modular sum enforces that the states appearing in a Hilbert space decomposition of that partition of this quantity Z have integral spin. So it is not obvious from this expression over here. H minus H bar is spin. Over here, it's some intermediate steps. You're integrating over all real values of H minus H bar. But what happens is that really what happens is that in this boundary effective action, there's winding modes, just like in the compact G case. And those winding modes have the effect of enforcing that H minus H bar is integral. So you have integer spin. Now, okay, so you get some non-zero amplitude. This strongly suggests that 3D gravity has an ensemble interpretation. We'd like to extract physics from this amplitude now. Yeah. So, not semi-classically. The spin, the spin could be 1. And that's, that's not a semi-classic. Semi-classics allows you to get things that are order 1 over g, but not order. So the fact that it's integral is really a loop effect.
If there is no saddle point, why do you even trust this? That the Chern-Simons path integral is a good approximation of what should be there?
So the Chern-Simons, so I presented the Chern-Simons to kind of set up an allegory, a way of thinking about the problem. But if really what we did was to integrate over gravitational variables. The only place where we used the Chern-Simons form was to solve the constraints that come from integrating out, like time components of fields. There's a separate question that you could ask, which is what would you get in Chern-Simons theory if you took a Chern-Simons theory seriously? Maybe this is what...
Okay, let me rephrase it in terms of gravity. How do you know that because you don't have a saddle point that most of the contribution are actually singular geometries or something that you don't really believe?
So how do you know that these things are... I'm not given the boundary values of fields, I can reconstruct a bulk metric. I've integrated out time components, so strictly speaking, it's like spatial metric, spatial spin connection. I can reconstruct the spatial geometry, and I can see, inspect, is it singular, is it not singular? And it's not. I mean, it's non-singular. But precisely when I have the right domain of integration for these B's. Okay.
Can I ask?
Oh.
So, two questions. So first, isn't h minus h bar being quantized? Isn't that like a condition on you've done a consistent quantization? Like
On what, sorry?
H minus h bar being integral. Yeah. Isn't that like a statement that you've done a correct quantization? Like
a state-dependent quantization?
No, a statement that you've done a correct quantization.
Oh, yeah. It's like the way I regard it is it's a consistency check of the whole computation.
And also, is the zero mode V, that's for like the relative Dane twists, right?
Yes.
Is it derived roughly the same way where you like do some regulated, like for the free boson you had just normal 1 squared and now it's like a regulated sum?
When these two are equal, there's like you can obtain it directly from like symplectic measure. Mm-hmm. But when they're not equal, you have to struggle a bit.
Okay.
You have. That is the subtle point of this entire, one of the major subtle points of this analysis. I can tell you more about it afterward if you're interested. There's physics hiding in here. What's the physics?
Can I ask another question?
Oh. Yeah.
Do you trust the region where big close to zero?
What, sorry?
When big is close to zero.
Ah, yes.
Do you still trust this integral?
Good. So here's the thing. This integrand is completely it's like JT. The integrand is completely non-singular near b equals 0. And what you can worry about is something you could worry about is as b shrinks to 0, that fluctuations of the phis become unsuppressed. That doesn't happen either. And in fact, there's once you perform part of the path integral that localizes b bar to constant values, these effective actions that you get then, the remaining effective actions that you have to do the integrals over, those partition functions, the one that produce these characters, you can show formally by localization that they're one loop exact anyway. Analogous to Stanford-Witten argument in the context of Schwartzian theory. It's like a quantization of Stanford-Witten in a sense, which is not at all obvious, I guess. It's fun to say the words, but it's not obvious why that's the case. Right, so physics, tau 1, these complex structures, they have a real part and an imaginary part. The real part is conjugate to spin, the imaginary part to energy. It is useful to Fourier transform in the real parts of tau 1, real parts of tau 2 to fix spins S1 and S2. And it's also useful to strip off, in these partition functions, if you were to interpret it in terms of a sum over states, many of these states are redundant. They would be Virasoro descendants of the primaries. So it's useful to strip off the descendants and just consider basically you can interpret the wormhole as contributing to a 2-point function of the primary counting partition function. In practice, that means stripping off the infinite products that appear in this result. And when you do that at S1 and S2, and well, now you only depend on beta 1, beta 2, what you get, the contribution from the wormhole, is very simple. It's 1 over 2 pi. This is like doing the modular sums. Kronecker delta, S1, S2, square root, beta 1, beta 2, over beta 1 plus beta 2, e to the minus beta 1 plus beta 2 times the threshold energy of a BTZ black hole with spin s, plus further corrections that are suppressed in the low temperature limit. And I flashed this formula because if you know about double trumpets and JT, you've seen a very similar expression there. In fact, if you use this analytically continue beta 1, beta 2 to imaginary value, complex values to get a form factor, you get a spectral form factor that depends on the two spins that is approximately T over 2 pi times this thing that, this threshold shift times Kronecker delta plus terms that are of order 1 over T. So there's fluctuations on top of a ramp. And you only see the ramp when the two spins are the same. This, I talked yesterday about spectral form factor, and the ramp for the presentation I give was in the context of models without a global symmetry. If you do have a global symmetry, expectation is that you have to look at superselection sectors, the identical superselection sectors, to see a ramp. That's what's going on here. Our spins are the same. So in other words, you get a ramp that's encoded in this wormhole amplitude, and it's precisely the one that you would have anticipated from random matrix universality. Maybe a way of summarizing all of this is that at least 2 points. One is that this gives quantitative evidence that 3D gravity, if it is a consistent theory of gravity, if it means anything, that it's dual to an ensemble. That, in some sense, generalizes random matrix statistics. And maybe another point that's worth emphasizing is that what the wormhole is encoding in this kind of language is the fluctuation statistics of that ensemble, the fluctuation, the level statistics. This gives another instantiation of an observation that we're used to, old story of Bekenstein and Hawking, that the Euclidean black hole encodes coarse graining of black hole density of states. What is the wormhole giving? It's giving coarse-grained version of level statistics, which is nice. It's kind of a mantra to hold on to. Now, going to the current day, there are some more things that have been done. One can look at higher genus boundaries. I mentioned already that those have been the subject of recent papers by Boleyn, de Boer, and then Chandra Collier, Hartman, Maloney. You can ask what those mean. That's a whole discussion. But there's more wormholes that have been discussed by now. And you could ask, in light of all this, well, what is the status of 3D gravity as a consistent or not consistent theory of gravity at this point in time, more generally? And the answer there, it's kind of unclear. It's a topic of ongoing research. The thing that you could worry about is, more complicated topologies. Does the path integral make sense? Is it convergent? Well, it turns out that, I think this is something that is understood by Lorenz Eberhardt and also by Alex Maloney, that at least if you consider spacetimes, Euclidean spacetimes of the form higher genus surface times thermal circle, that in those cases, once you consider almost anything more complicated than what we did, I guess with n boundaries, I think genus 0, 3 boundaries is okay, but just about anything else, the moduli space integrals do not converge. In other words, the wormhole amplitudes diverge. And what does this mean? We don't know. And the reason, if there was a single CFT dual to 3D gravity, that would be fatal. There's a wrinkle, though, in that it looks like 3D gravity, if it means anything, it would be an ensemble. In which case, the statement that these amplitudes diverge would be a statement that these averages in the ensemble would diverge. And while we know many examples just in sort of first-year probability theory where that happens and we don't worry about it. Consider a distribution in one variable with random variable x. That's a perfectly well-defined probability distribution. It satisfies all the axioms that a distribution has to satisfy. But if you consider any non-one moment of x with respect to that distribution, it diverges. Right? So it's unclear, I guess. It's a topic of ongoing research. Does the divergence of these amplitudes in 3D gravity, what does it mean for a possible duality? Yes, there's a question.
Yeah, just wanted to ask a question about the SFF story. So is there any ongoing research or chance to get the plateau as well? That seems to give you the ramp, right? So
what is to get the black hole?
No, to get the plateau in the SFF.
Oh, to get the plateau. Yeah. So the first target that people have been making for trying to find plateau is in JT gravity, where it is currently an outstanding problem. I would do JT before this. Yeah. Okay.
What was this result again? The sigma, like you can't do a consistent quantization on this background? The sigma gn times S1?
Well,
is this written down?
I have not, there's allusions to it in papers. Eberhard has this off-shell paper from earlier this year. There's one of Alex's favorite papers from 2015 on quantization of chiral gravity, where I think similar comments appear, but it has not been, I wish they would write things down. It's something, it's sort of, it's well known to those whom it's well known. It's at that kind of a point. Right, so in maybe the analog in JT is, imagine if the Weil-Peterson volumes diverged. That's the problem. Right, so what I wanted to do was to talk about more than 3D gravity. I wanted to go back to, higher dimensional ADS-CFT and supergravity and whatnot. And it seems that I have badly used my time, or maybe this was very interesting to some of you. Some combination of those two things. So let me make a few comments about the status of things in higher dimensions. What did we do? I already talked about ADS3. We saw that these, for these kinds of boundaries that we were considering, so, S1 in that case times another circle, so that we had a torus. But in higher dimensions, you could consider, thermal circle times either a torus, spatial torus, or a sphere. Well, in those cases, there are no on-shell solutions of Einstein gravity, supergravity, whatnot, that would have two boundaries connected through the interior. I guess I should say Euclidean. So this is still an off-shell problem. And how do we begin to organize physics off shell? That's kind of been the theme of the work with Jordan from the last few years. And one way to kind of begin is to go back to these wormhole amplitudes in JT and 3D gravity. You know, they have the structure of a moduli space integral. You know, either in JT or in 3D gravity, roughly speaking, you have an integral over moduli times a classical action of the wormhole at fixed value of the modulus times loop factors. And maybe with terms that 2 loops, 3 loops, and so on. In JT and ADS3 gravity, you get 1 loop, there's no higher loops. And in those cases, you know, you can actually perform the integrals, they converge, you get some non-zero result. That's how it works there. You have so the words you could say are the wormhole amplitude is a moduli space integral where the modulus is like the size of the bottleneck. And in higher dimensional gravity, I guess I just have enough time to quote the result and not argue for it. The best we can do is to find a way to represent the sum over off-shell configurations in a similar form, an integral representation. So for instance, if we're talking about, you know, as an example, S1 times S3 boundaries in asymptotically Euclidean ADS5, then formally we can use some calculus called the method of constrained instantons. This comes to us from people like Affleck and Affleck-Seiberg in the 80s, which allows you to, in gauge theories, to discuss phases of gauge theories where you don't have instanton solutions to the equations of motion, but you have near instantons, and you'd like to sum over them. And for instance, famously in NF equals n minus 1 supersymmetric QCD, those near instantons generate the superpotential. You can do real computations using these things in that setting. So you can use this method formally to produce an integral representation for the sum over Euclidean. You know, we have to say what the rules of the game are. So what are the rules that we're abiding by? We're trying to sum over Euclidean non-singular metrics and the result that we find is that formally such wormhole amplitudes can be written as an integral over a modulus. You could call it B. I'm going to call it E here. These wormholes have a modulus B. You can think of as size of the bottleneck. You can recast it in terms of the energy perceived on the boundary of these geometries, E. The two energies end up being equal, so we can call them one and the same. In this case, B, that energy is proportional to B to the 4 over g Newton, so you can trade B for energy. At fixed value of modulus, wormhole has an action that can be computed. It's just the holographically renormalized action of the wormhole. This is e to the minus s. There's a one-loop determinant that we don't know how to compute. We know how to in JT. We don't know how to in higher dimensional gravity. There's 2 in higher loop corrections. But the thing is, because these things are off-shell, you have to integrate over all of them. the way we get this is by, the way this method of constrained instantons works in gauge theory is you drop an insertion of the identity into the path integral. You use 1 is integral over a Lagrange multiplier e to the I lambda some constraint functional of the quantum fields minus c. Formally, that's 1 for any constraint c. So you drop that into the functional integral, and effectively what you do is you're taking field space and you're labeling it by hypersurfaces of fixed constraint. And what can happen for judicious choice of constraints is that at fixed value of constraint, you have a saddle point approximation even though the whole thing doesn't. That's how you find these wormholes. And then what you have to do at the end of the day is to integrate over all possible values of the constraint to ensure that you really inserted 1 into the path integral. In gauge theory, this can be done. In gravity, well, if you follow the steps, if you treat the sum over metrics like you would a sum over non-singular Euclidean metrics, the way that you would sum over field configurations in field theory, formally, this is what you get. And I guess I should have said this E naught. This is the energy, the smallest possible B that you can get. It's the limit where the wormhole pinches off. And you can map that to the threshold energy of the lightest black hole with that boundary topology, S1 times S3 or S1 times torus, what have you. Formally, this is what you get for the wormhole amplitude. What do you learn from it? What I learned from it is really 2 things. The first thing I learned is that the full wormhole amplitude, in a very precise sense, is inaccessible in bulk effective field theory. In other words, I regard this expression as an organizing principle. I mean, I don't know how to compute. The only thing I know how to compute it in is this and to give this representation. So I treat this as an organizing principle. What this teaches me is that the amplitude is dominated by a regime in the wormhole moduli space where the wormhole is pinching off. Those are the contributions of least action. And those are precisely the configurations where the geometry becomes strongly curved, bulk effective field theory breaks down, and I have no control. So I went through all this analysis to find out that bulk effective field theory doesn't tell us a lick about the amplitude, the full amplitude. This is not a bad thing. This says, whether the wormhole contributions, whether the connected contributions to the amplitude vanish or are whether factorization is violated or not, is really an ultraviolet question about the non-perturbative definition of your theory in the bulk. So whether or not, in other words, factorization is really a non-perturbative question, whether you have factorization or not. The other benefit that you get from this, and this is where the work in the present day kind of starts, is that there is a way, if you think about this wormhole size or this energy as a modulus, well, we can start saying words like, can we stabilize that modulus? Can we stabilize the moduli? The answer is yes, we can. And then we can get a non-shell wormhole, but a non-standard one. The way to do it, oh, yes.
So if we want factorization, we want these disconnected geometries.
Yeah, if we want that, well, if we want factorization, we want to say, connected part of multi-boundary amplitude vanishes.
Right.
And what I'm saying is that connected part is UV sensitive.
Right. So are you saying, okay, so when you say it's UV sensitive, it means I keep adding all these like different connected like topologies and everything.
Sure.
And
you
they
can,
may cancel to be zero or individually be zero.
I mean, you
or
have
something?
all manner of things show up at that energy scale. You have other topologies, you have these singular regions of moduli space. In string theory, you have non-geometric configurations.
Right.
Yeah, they all come in at the same order. And the expectation would be that, and I guess this now history is cyclic, somehow, some way, everything's fine.
Okay. They all cancel each other.
This is a hope that one can voice. Whether or not they, I mean, ideally one wants to compute the things and see what happens, but the problem is we lack the technology to do so.
Okay.
The point of this exercise is to, localize what is it that we need to compute. The problem is it's, non-perturbative physics in the bulk, which we presently don't know how to access.
Thank you.
Forgetting about non-perturbative physics,
Yeah.
like even perturbative corrections could start matter, like this two-loop term or higher loops.
Sure.
In the strongly curved.
Yeah. You can do some, you could worry, maybe those, I guess what you're saying, you could wonder if those can offset the leading dependence. And, I mean, this is analogous to, the analog of that in quantum field theory, and this can sometimes happen, is where you can balance like treat-level physics against loop-level physics. There's some instances where one can do that, or where you can balance like one loop against two loop. Like, what is it? Like physics of the conformal window, near the edge of the conformal window is a great example of this. But here, you need a parameter in the game that kind of allows you to balance those effects against each other. Naively, everything's just suppressed and you have no way of having balance, at least for large energies. But again, I mean, it's a theoretical possibility. One would need to compute the corrections to see. I have no idea how to do that.
I mean, I would raise an objection to even writing down this expression maybe just because in higher dimensions we don't have renormalizability.
That's right. I mean, even around a fixed, such geometry, a fixed energy, you don't have, you don't have renormalizability, but you can still treat gravity as an effective theory in that setting, and you can say the words anyway.
Sure. Yeah. Thanks.
Yeah. I can't give precise answers because it's not known. Some other people should work on it too, not just Jordan and me. So, although admittedly it's been very fun but also extremely confusing subject to work on. So. Right, so can we stabilize the energy? Answer is yes, we can. The thing that helps you, the only direction in field space that these wormholes are not stationary with respect to, that you have to fix, that you have to pin down, is the total energy shared by the two boundaries. So if you divide up all the directions in field space, there's fluctuations of bulk fields, and there's also fluctuations of boundary energies. By boundary energy, what do I mean? I mean like the space-time integrated, energy density on the boundary that you would get from the holographic stress tensor on that boundary. E1 minus E2 is a fluctuating variable in this setting, which has a saddle point value at 0. But E1 plus E2 that's the modulus that labels these wormholes. But the point is that E1 and E2 are both boundary data. They can be fixed by a boundary condition in gravity, where you fix boundary metrics and also certain components of boundary stress tensor. In other words, you can drop in a boundary condition that pins that modulus down to some total value in the sum over metrics, and that has the effect of stabilizing the wormhole at whatever total energy you want. That has two consequences. One is that because we fix something that depends on both boundaries, we've correlated the two boundaries in some way. If you think of the two-boundary problem, you might hope that this computes something like product of partition functions. And you write that as a double integral over density of states. We're dropping a delta function in here on the boundary. And that quantity no longer factorizes. Depends on both replicas simultaneously. So it's, in other words, the wormhole that you find this way, you puff up, you stabilize the moduli, it doesn't contradict factorization. The second consequence is that the stabilized wormhole still encodes physics, in particular the ramp and spectral form factor. There is one way of saying what we're doing with fixing total energy, we're studying microcanonical physics instead of like canonical ensemble. And there are microcanonical versions of the statements that I made yesterday about the ramp and spectral form factor. And so this and if you churn it through, this stabilized wormhole, fixed total energy, still describes a ramp, still matches expectation from quantum chaos, doesn't contradict factorization. Yes? Oh. Oh, okay.
Hello? Oh, nice. Microcanonical ramp thing, like a single element of the ensemble, like this crazy curve that you drew yesterday?
Yeah, good. So what this encodes is this, when I say it encodes a ramp, I mean something smooth. So you get a smooth microcanonical ramp out of this. And the smoothness implies something. I said last time that in the quantum chaos literature, for a single instance computed exactly, you get, you tire your arm out drawing it. To get a smooth curve, some averaging must take place. But the thing is there's an ambiguity as to what kind of averaging it is. In the quantum chaos literature, it can be an average over couplings, even by a little bit, that's enough. It can also be a smearing in the energy domain. I think I said this yesterday. That'll accomplish the same goal of giving you a smooth curve, but smearing in the energy domain introduces fluctuations that oscillate at the smearing scale. Maybe this is a good place to leave off. So we get a smooth curve. This indicates some averaging in gravity. But because the wormhole doesn't contradict factorization, we don't actually know what kind of averaging it is. In other words, bulk effective field theory tells us that there's averaging over, well, something, couplings or energy windows. Non-perturbatively small energy windows will suffice. This would be consistent with ensemble. This would be realizable in a single instance. Bulk effective field theory produces these smooth curves that tells us that there's some averaging, but it doesn't tell us the nature of the averaging. To access the nature of the averaging, at least in this setting, is a non-perturbative question. A smoking gun would be the full two-boundary amplitude. Does it have a connected part or not? But that's, as I've tried to stress, that is beyond the accessibility, what you can access in effective field theory. And these kinds of words, how to say that, you can smear, or that maybe there's some averaging over couplings or it's ensembles. It's funny, those are the same kind of words if you trace the history of like thermal physics and statistical physics, dating back from Boltzmann to ETH in the present day. You construct the thermal ensemble as kind of a means to efficiently compute averages in equilibrium systems, and it works very, very well, even though, you know, the quantum state of our universe is pure. And the reason why it works very well is because those two things, whether you're in pure state or in the ensemble, really differ by non-perturbative effects in the thermodynamic limit. We're saying something very similar here at the end of the day. It's lunchtime. Thank you for your attention. Right, good question. So something that would contradict factorization is if you keep the saddle, but you constrain the two boundaries independently. It's an excellent observation. What ends up happening, this is not obvious from what I've written, but if you end up constraining, the two boundary energies separately, unless you constrain them to be exactly the same value with a perturbatively small difference in 1 over n or something, then you lose the saddle. You lose the wormhole. Yeah, like what happens, one way of saying it, suppose you just try to fix like energy on one boundary, as an example. That would, from the boundary point of view, you just fix E1 to something, maybe within a window. What happens then is, because E1 minus E2 is a fluctuating variable in this geometry, that pushes the saddle point value of E2 away from E1, and then all hell breaks loose. All manner of other fluctuations of the gravitational fields now have a little bit of pressure and start condensing. Somehow it's precisely this combination that is the right one to stabilize. We don't have a proof that this is the only way to do it, but this is the observation.
One more question and then lunch.
Yes, good.
So I have a very naive question is, when you consider offshore calculations, would you expect factorization? Like, shouldn't that be a non-shell?
I mean, in proper ADS CFT, if we had the power of God and were able to compute these things non-perturbatively, then, if we're talking about n equals 4, then I would expect, there's very good reason to expect things factorize. One reason why, maybe, people have talked about, okay, maybe you can average over Yang-Mills coupling or over other things. One can take a step back from n equals 4, change the question slightly. Let's go up in dimension even further and talk about M5 branes. The virtue of doing that is that in the 5 brane, from the gravitational point of view, ADS 7 times S4 is, from this point of view, it's basically the same as ADS 5 times S5. But from the boundary perspective, 2, 0 is very different from n equals 4. It has no adjustable parameters whatsoever. It's an isolated CFT. There's nothing that you could even try to average over. And yet you see the same kind of paradoxes in the bulk regarding factorization and whatnot. So from that point of view, I would expect that, for proper ADS CFT, there's, it's this.
Okay. The second question was, you said...
I guess I should say, that's my opinion. It is in the field of ongoing research that is welcoming to young people.
And the second question was, do you have any comments about the calculation, I think by Eberhard, on these three zero genus, 3 boundary terms? There are 3 boundaries, so they're particularly special, I suppose.
I don't have... I've been wanting to ask Lorenz about it, and I haven't had I don't know. I don't have anything intelligent to say. I'd like to see, for instance, an expression for that volume of moduli space somewhere on the archive, and it hasn't appeared yet. Yeah, in JT, I mean, it's in some sense like 1 is the volume, but what is it in the higher dimensional setting?
All right, let's thank the speaker again.